Here's one more example that ties everything that we've learned so far together. So I've got a scientist that combines 5.00 moles of Fe and 5.00 moles of O2. It looks like the same number, so that should be easy, but first we have to look at our equation, okay, in a reaction container, and we want to determine the limiting reactant and justify the answer using calculations. So we're going to show our work and make sure that it's obvious what we did and how we determined it. Okay, so don't forget that when you're finding the limiting reactant, you take the number of moles that are given and divide it by the number of moles that the reaction coefficient indicates. So I have 5.00 moles of Fe divided by our coefficient for Fe, and the equation is 4 moles of Fe. All right, when I do that, 5 over 4, 5.00 divided by 4, and I'm going to keep 3 sig figs because that's what I was given. It's 1.25. Don't forget, this is not moles of Fe. Moles of Fe canceled out. I don't have units. If I want to write units, I would write moles of reaction. And you don't have to write those units. Okay, 5.00 moles of O2 divided by our coefficient for O2 is 3. 3 moles of O2. So 5 over 3. I get 1.67 to 3 sig figs. And again, that is, if you want to write the units, it's moles of reaction. Or you could say batches. But don't put moles of O2. Those units cancel out. Okay, what are the substances that should be in the reaction vessel at the end of the reaction? First of all, we need to decide. I didn't identify the limiting reactant yet, did I? I just did the calculation. Now we need to take the time to identify the limiting reactant. So we look at these two answers and we pick the smaller one. 1.25 is the smaller of the two numbers, right? This is our smaller number. Since that's our smaller number, that tells me that Fe is my limiting reactant. That's your answer. If you don't do that, you haven't actually answered the question. What are the substances that should be in the reaction vessel at the end of the reaction? So after it's completely finished, as much as possible, what should be left? Well, Fe is used up. It's our limiting reactant, so it's gone. I should have the excess reactant, which is O2, and I should also have some product, which would be Fe2O3. So the substances in the reaction vessel are O2 and Fe2O3. Again, what's left in the reaction vessel is always the excess reactant and any products that are formed. Okay, based on the amount of limiting reactant, determine the moles of Fe2O3 that can theoretically be produced. So what should be produced, what's our theoretical yield, is what that's the technical term for it. Well, I always am going to start with one of my givens. I need to use the limiting reactant, always. So we're going to do 5.00 moles of Fe over 4 moles of Fe. Set that equal to what I'm looking for. I'm looking for X moles of Fe2O3. That's what we're looking for, is moles of Fe2O3. What goes on the bottom? We have to look at our equation and find Fe2O3. 2 moles of Fe2O3 goes on the bottom. Then we would cross multiply. I end up with 4x equals 2 times 5 is 10.0, keeping the 3 significant figures. And then if I want to solve for this, I need to divide by 4. Divide by 4 on both sides, so that cancels out. So x equals 10 divided by 4. Don't forget to keep 3 significant figures, so it should be 2.50 moles of Fe2O3. All right, now it says to calculate the moles of excess reactant that are consumed. So to find out how much I've consumed, how much of the excess reactant I've consumed, I'm going to use this same exact process as step C, except my unknown X is going to be the excess reactant. So let's start with our limiting reactant. As always, 5.00 moles of Fe over 4 moles of Fe. Once you figure out what your limiting reactant is, that's your given in every step from now on. So I just copied what I had right here because I knew that was my limiting reactant. Okay, now my excess reactant would be the other one. This is excess, oxygen is. So I want to know how much, I don't care how much I had, I want to know how much I used. Oxygen becomes the new X. So X moles of O2, that's our excess reactant, over, and for O2, coefficient is 3, so 3 moles of O2. Cross multiply, you end up with 4x equals 5.0 times 3, that's going to be 15.0. Divide both sides by 4. End up with 3.75. Check your units. Moles of O2. After you've solved it based on the problem, double check and make sure it's what you were looking for. I was looking for moles of the excess reactant, and our excess reactant was O2. So moles of O2 that were consumed or used. The moles of excess remaining, that means I need to know how much I started with minus how much I used. So available minus consumed. Go back up to find out what was available in the problem. In the problem I said that I had 5 moles of O2 available. So there were 5.00 moles of O2. I used 3.75 moles of O2. That's going to tell me the moles O2 that remain. So 5 minus 3.75, end up with 1.25 moles of O2. All right, after calculating the reaction, or after the reaction is complete, so this is another part of our problem, after the reaction is complete, the scientist collected, so it sounds like a real experiment, he collected 2.00 moles of Fe2O3. This sounds real. This is my actual yield. Calculate the percent yield of Fe2O3 produced. Well, we need to go back and look at the theoretical yield for Fe2O3. We thought, theoretically, we should be able to produce 2.50 moles of Fe2O3 theoretically. That's our theoretical yield. It wants us to find the percent yield. Okay, percent yield is actual yield over theoretical yield times 100%. That's the formula. Actual over theoretical times 100. So our actual yield is 2.00. Make sure you're looking at the right substance. It's Fe2O3. And then I'm going to go up and find the theoretical yield again. The theoretical yield is 2.50 moles of Fe2O3. And then we're going to multiply that by 100. So we have 2.00 divided by 2.50 times 100, and I get 80%. So this is an 80% yield. All right, now try your hand at the practice problems and let us know if you have any questions.